Hello, everybody. Thanks for spending time with us. So today, I'm going to have a brief introduction of the DOE ORNL heat pump design model. And I'm a researcher from Building Technologies Research and Integration Center in Oak Ridge National Lab. And the heat pump design model, the acronym is HPDM. HPDM. It's a public domain software supported by DOE, mainly by the Building Technologies Office. And this is a thermal system design and simulation software, and it's public domain. And mainly work for vapor compression system design and optimization. And at first, we want to acknowledge and give our thanks to our sponsors and the Department of Energy Building Technologies Office, and specifically the thanks to our Technology Development Officer, Mr. Tony Buza, for his long-term support so that we can come to this stage. For this introduction and also some other following presentations, we are going through the general features of the heat pump design model, and we will also introduce a web interface that everybody can access, and the Excel interface that you can download the software at your computer and run with it for the more comprehensive and detailed simulation. And then we will illustrate the program structure of this public domain software, as well as a typical project simulation folder. And first, we want to talk about the general structure of the ORNL heat pump design model. It's not a fixed configuration system design and simulation tool. Actually, it's a component-based flexible modeling platform and can work for numerous extensive vapor compression systems. And it has a component-based modeling structure, and it's based on extensive component libraries. And in the library, we have heat exchanger models, compressor models, and the fan pump models. And all the component models, they follow some strict grammar, and they have standard interface. And the user actually can select them, and in plug and play feature, and user define them and define the connection, and then the solving framework will automatically interpret the connection and group all the selected components into a system. So you can see actually this is a component-based modeling framework, and we don't develop system configuration specifically. We only develop component models, and actually the system configurations are constructed on the fly. So in this way, this will promote great productivity and extensive modeling capability. And using this tool, and the major user base is for the heating, ventilation, air conditioning, and the refrigeration industry. And we already modeled in our research projects for the advanced refrigerators and the heat pump and the water heating, heat pump water heating, and the rooftop air conditioners, and also like for complicated system configurations like integrated heat pump and ground source and air source integrated heat pump, or multi-terminal, multi-components, variable refrigerant flow system. And as we mentioned, we have extensive component libraries. For example, compressors and heat exchangers and fan and pumps and the desiccant and different geometries of the heat exchangers. And the models were developed based on detailed physics, detailed correlations that we can account for various tube and fin geometries. For example, the microfin tubes and the microchannel tubes and the twisted tubes and the different fin types. For example, lure fin, smooth wavy fin, and convective lure fin, and so on. And this is a thermal system and components modeling tool. It describes detailed physics. For example, the water condensation and the coil entering non-uniform airflow distribution and correlate extensive refrigerant and fluid properties and consider two-phase flow patterns. And because this is mainly for vapor compression system modeling, so we have a capability, enhanced capability to handle hundreds of working substances in the HVAC and R industries. For example, air, water, glycol, CO2, HFC, HCFC, and so on, natural substances. And we can, for the refrigerant properties, we can handle refrigerant mixtures. For example, the zero tropic refrigerants that they would have the glide changing with the refrigerant quality in two-phase region, and we can also handle the subcritical and supercritical refrigerants like CO2, and not even mentioning the air psychrometric properties as well as the glycol and the water properties. And the heat pump design model, we focus on the building equipment vapor compression system modeling, but it has established connection with other building energy simulation tool and as well as the detailed CFD simulation software. And we call this smooth engineering analysis flow, and we can directly deliver the product design from the concept study to a life cycle analysis for the eventual economic and marketing analysis. And the heat pump design model is a collection of the component component model libraries, and we can accept the boundary conditions and from the CFD simulation as input to the detailed heat exchanger modeling, heat exchanger component models, and we put the detailed component models in the system, and we provide the system simulation performance, and then the system equipment performance can be integrated to other building energy simulation software like Modelica in terms of the dynamic link library, and we can also generate performance curves and to be input to any class, as well we also can generate performance tables to be used by the transit or energy class. Okay, and next we will introduce web interface.